So Monday we delved into trees, specifically talked about binary trees. And the first methodology we used was the depth first traversal. And then we had different examples of the three different types of traverse. There's the pre-order, the in-order, and the post-order. So we went over that on Monday, recapped it on Wednesday. So let's start here with the breadth first and finish our binary tree searching. So here, the breadth first, instead of trying to go all the way as far down to the left as possible, you just start at the top from left to right at each level. So what that does is this explores the roots there, the nodes that are nearest to our root before going into further. So in this case, the order would actually be Alpha Romeo Charlie, Delta Echo Foxtrot Golf, and it'll just continue down through that tree. So an example of a question on an exam or an foundation exam, if you take that block, they would ask you specifically based on this binary tree, what order would each of these nodes be visited, if it's on a breadth first traversal, or if you're asked a depth first traversal. So if I was doing a depth first traversal, what would be the order of our traversal if we did a pre-order? What does the pre-order mean?
Do the first root first. Root first?
The root is first, right? Is everyone tracking on that? You always do the root first on a pre-order. Remember my little drug deal analogy? The alpha was on the root, and that money was go by chart, right? Okay, so if I was doing this as an in-order traversal, when would the root be visited? Anyone else?
After the left side's done, or the left?
B?
So what would be the first three notes? If all we had was Delta, Hotel, and Lima, what order would it be? An in order.
B A C.
Yes. It'd be in the middle, right? The in order. So the root node is visited in the middle of the left and the right. Sorry, guys, remember that? So if I do a post order, when is my root visited?
Last.
Very last. Okay. So you just need to make sure not only which traversal methodology are you using, are you doing breadth first or depth first? And then if you are doing depth first, you need to know which how the root node is visited. Is it pre-order, in-order, or post-order? So you need to keep track of those different methodologies. So in a breadth first traversal, it literally just starts at the top and it goes from left to right for each row or each level. So there is no other traversal methodology for breadth first. So it doesn't have like the depth first, it doesn't have those three different ways to search. It only searches one way on the breadth first. So when we are dealing with a breadth first traversal, and you want to write the software in order to accomplish that, how would you actually do that? Here, what happens is you enqueue its root node. And while there are more nodes in the queue, you're going to dequeue the node at the front of the queue, print that out, and then enqueue its children if you can. And so again, left then right. You always go from the left and then to the right. So we talked about earlier this semester why binary searching is more effective. And why is binary searching more effective? What makes it efficient? What is unique about doing a binary search?
Cuts it in half.
It cuts it in half for every iteration, right? Linear searching, it just goes from left to right or right to the left, depending upon the order of your index. But in a binary, it finds the middle, and it halves it. And so for every search, you only are searching half of what's left over. So if we're searching this binary tree here with a value of 23, what half of the tree would I first start out looking for? What half of it? How would I find out where I need to start looking?
Compare the subroot value to the root value.
Okay, so what happens is you look at the value of the root, all right? And you're going to go, is my 23 larger than or less than the root? And that tells you whether you're going to go down on the left or go down on the right, correct?
Yeah.
So 23 is larger than the root. So obviously we got to go to the right. Does that make sense? Because if we were looking for the value of 5, which side of the binary tree are you going to search for the value of 5? The left, because 5 is less than 3, correct?
Mhm.
So that's what makes binary tree searching so efficient, because you can lop off half of your binary tree the very first time through, because you just find out what the value is at the root node. So when you're looking at binary trees and we're talking about trying to set up an algorithm to search them, you just check whatever that value is and you do a comparison against the root node's value. So we look at what's on the root node. So whatever value you receive, is it greater than or less than the value of 8? And so we end up doing a half. So again, don't forget, when you are halving and we are considering the big O, what has the most significant impact from our binary tree search, that order from a big O perspective is log n. And those are just the common orders that are in our previous slides when we were first talking about big O. And so that is just the rule that applies to doing the binary searching or the halving. So all the data values in our left subtree are always going to be less than the data value in the node itself, in the root. So again, if you look at this tree, so 3 is definitely less than 8. Then we get the value of 1. Well, 1 is less than 3. But then you see that we got the value of 6. 6 is less than 8, but it's greater than the root node of 3, so it gets pushed over to the right side of the 3. Does that make sense? So now we have our values of 4 and 7. 7 is greater than 6, so it has to go on the right. 4 is less than 6, so it has to go on the left. That's how binary trees are established. They're based on those rule sets. So you see all the data values are on the left subtree. They're all less than the value of 8 at a root node. All the data values in the right subtree of each node are larger than the data value of the node itself. So now when we look at this again, the value of 10 is greater than 8, so it has to be on the right. And then we have the value of 14. 14 is greater than our 10, so it has to go to the right. Then we get down to where we have a value of 13. 13 is less than 14, so it goes on its left. Does that make sense? Less than, always to the left. See the alliteration that goes there? Less than is left. Okay? I know it's silly, but you'll remember it. Actually, you probably remember the drug deal conversations better, won't you? So think about this. Remember that, yes, we have a left subtree, and we have a right subtree, but each of them has their own children that are dependent upon it. So each subtree could potentially have more than one subtree to itself. So here's a subtree of 3, and it has another subtree that has 6 as the root node. You see that relationship there? So 3 has a left and a right, 6 has a left and a right, and then the 8 has its left and its right. So all these values here are all considered subtrees. So for every node, if it has a child, the rules still have to apply, even if it's just one child. If I came down here on my 14, and I had a value of 16, where does the 16 go? It's going to go to the right of the 14, isn't it?
Yep.
Because it's greater than 14. So those are the rules that we have to follow. So here's another binary search tree that has a lot more nodes in it. And so we're looking at this binary search tree trying to figure out what's going on with it. So you see that our root node, its value is 44. Everything to the left is less than 44, isn't it? Everything to my right is greater than 44. Does that make sense? If this layout was, if it wasn't true, if this was not laid out this way, it would not be a binary tree. What makes this a binary tree versus just a tree itself?
Each node has 2.
Values are organized.
Because the data in the tree are following a very specific pattern, where every value that's on the left of a node is less than the node itself. Every value that's on the right of that node is greater than the node itself. And so, because when it follows that pattern, you can look at this and you can go, oh, that is definitely a binary tree. You know, yes, the words are there too, but you know what I'm saying? If I just drew a tree up there without the text on the screen, you would identify the fact that this is a binary tree because it's following that pattern. Does that make sense? Okay. So, the abbreviation for binary trees is BST. So sometimes you'll see on exam questions BST, and you're like, Whiskey Tango Foxtrot. Okay, it's a binary search tree. Okay, so it's very, very efficient for searching because it just keeps having how much data you have to look at for each iteration. So what happens is you are embedding the binary search into the data structure itself. So it makes it pretty easy, doesn't it? And so the root of every subtree of BST on the previous page is the root of BST. And so here, when we have our ordered nodes in our tree, that means when we insert nodes into our BST, they are not just randomly pushed in there. You know, there's a specific order that has to follow. So there is a specific way to insert. So that's one of those things that. All right, so here. We're looking at this binary tree, and I give you the value of
22. That's supposed to be on the right. 22.
So is this binary tree set up correctly?
No.
Why not?
22.
Looks like that.
20.
What's wrong with it?
The children are, it looks like children are larger than the parents.
The value to the left of the 3 is bigger than the node itself, right? It's 13. And then you're like, you look at this, you're like, well, that's not enough. Is it? Okay, so we look at this one. We have another issue here.
But if they ask for pre-order, do you still just go through it the normal way?
You have to know what methodology you're using. Is it breadth first or depth first? And if you're doing depth first, are you doing pre-order, in order, or post-order? Okay. So from a binary tree perspective, can we use the log n methodology on this tree right here? Will it allow us to use that? We can't, can we? Because our root node is 3, its left is 28, its right is 13. So all of the data that's on the left already violates the binary tree rule. So if we're doing a pre-order traversal on it, then we have an in-order traversal and a post-order traversal. And then there's those as well. All right, so let's look at this. Pre-order traversal. What would the order be? Pre-order. What does pre-order mean?
Root first.
Root node is first. Okay, so I have no whiteboard. It's really irritating. All right, so I'll just do this by hand. All right, so if the root node is first, so my first value is a 3, correct? On a pre-order. What value follows the 3 on a pre-order?
13.
13, so that's on the left, correct? What's after the 13?
22.
22? Who thinks it's 28? Why would it not be 28? Because, so pre-order, in order, and post-order, what methodology are we searching with? Is it breadth first or depth first?
Depth.
Depth first. What does depth first mean?
Go to the left.
Go as far down the tree levels as possible on the left. And once you exhaust everything on the left, then you can move to the right, correct? Okay, so if we're doing a pre-order, pre-order implies depth first. So we need to keep searching our binary tree all the way down until we find a leaf, correct?
Right.
So if I'm doing a pre-order So we've got our root node of the 3. So he's the first one that always gets checked. Then we go to the left. The left has a 13. Is that a leaf?
No.
Is 13 a leaf?
No.
No. So what would the next value be that we visit?
22.
22. Because we keep going as far down as possible until we exhaust everything on the left. So the next value is 22. After my 22, what's going to be visited?
19.
Our 19. After our 19, what's visited?
26.
26. After 26,
54.
54. What's after the 54?
71.
71. Why?
You've done exhausted the left. So
We completely exhausted the left. We found a leaf. We found the end of our binary tree on the left. The end of it is a 54. I asked you for pre-order. So pre-order does the root node first. So when you're looking at just this triangle right here, the parent with its 2 children, pre-order says I do my root node first, 26, then I do my left. Now I can do my right. So that's my 71. So we're done with this here. So we're going to go back up 1 level to our 19. Does our 19 have a right?
no.
So are we done with that level?
Yes.
Okay, so we go up to the 22. Does the 22 have a right?
Yes.
What's its value?
33.
33. So we're going to print that one next. Looking at 33 as a parent or as a root node, we have to look at the left and the right again, don't we? We go as far left as possible. So 33 is a root. Who's his left? 14. Does 14 have children?
Yes.
So we need to follow its children, right? What is this child? It's on the left. Our 11 is on the left, so we can deal with that. So we found another leaf. We found the final depth of our binary tree on this left. So you're looking at 14 as a parent, and you're looking at his children. So we found 11 as his child on the left. We've already visited 14 because we say it's pre-order. So the parent node here gets printed first, and then it's left. Then we go to its right. Is there anything for us to visit on the right?
No.
No, he doesn't have a right. So we're done with 14. So we go back up to our 33. So we've exhausted the left of our 33. What's on our right? We have an 87. 87 has children. So which one am I going to visit first?
8.
The left. So that's an 8. Is 8 in a leaf?
Yes.
Yes. So now I can do his right on the 87, can I?
Yeah.
So his right is 56. So we're done with the lowest level here on this right. So we roll back up, we have completely exhausted the left of our root node of 3. Haven't we?
Yes.
We visited all the nodes. So now, on our 13, we have a right. Have we dealt with the right on our 13 yet? I mean, everything we've done so far has been all of this over here. Just the left of 13. You still have to deal with the right of 13. So in that case, then we would go to our right, which is 9. And now we look at 9. Is 9 a parent node to anybody?
Yes.
Yes. Does he have a left?
No.
No, so we don't need to put anything out for that. But he has a right, so we need to check his right. So that's a 75. So the entire left of the root node 3 is done. So the rules say that on a pre-order, I do the parent, the left, and then the right. Who is 3's right? We have 28. Is 28 a parent? Yes. So which way do we go first?
Left.
To the left. So what's our next number? We have a 15. Is 15 a parent?
Yes.
Does he have a left and a right?
No. Just
He just
a
has a left. Okay, so we have a 10. Is 10 a parent? Does he have a left and a right? Just a left. So we're going to deal with his left, which is 63. If he had a right, we would do that next, but he doesn't. So we're done with the node 10. Value of 10 is a parent. Roll back up one more. We look at 10 being a parent. No, if we look at 10 as the child of 15, does 15 have a right? No. So we're done with 15, correct? So now we roll back up to 28. Does 28 have a right? Yes. So now we need to deal with its right. Its right is 36. Is 36 a parent? Which children does he have? So which way do we go next? To the 7, because it's his left. Is 7 a parent? Yes. So his child is 69. Is 69 a parent? Yes. So does he have a left? Yes. So we deal with his left. We found the leaf. We're at the end here. So we've done the parent of 69. We printed him. We've done his left. Now we need to do his right. His right is 68. We're done with the node 69 as a parent. So he is a child to 7. Does 7 have a right? He doesn't. So we're done with 7. So we're going to deal with 7 as a child of 36. 36 has a right, which is 44. So let's see if we're actually correct. On a pre-order, we had 3, 13, 22, 19, 26, 54, 71, 33, 14, 11, 87, then 8, 56, 9, 75, 28, 15, 10, 63, 36, 7, 69, 59, 68, and 44. So we got that one right. So the pre-order is kind of easy, right? It's the in order that's a pain in your ass. So let's walk through the in order. What does in order mean? When is the root node visited? In the middle, right? So our root node is a 3. So who are we going to visit first? 13. But is 13 a parent?
Yes.
So are we going to deal with him yet?
No.
No. Where are we going to go next?
22.
22. Is 22 a parent?
Yes.
Then we can't deal with him yet, can we?
Nope.
So now where?
19.
19. Is he a parent?
Yes.
Yes. We can't deal with 19 yet.
Yeah, well,
Just kind of like going backwards, essentially. Kind of.
What we're trying to do on an in order is go as far, as deep as possible on the left to find a leaf. We got to find the leftmost leaf, if it exists, before we can start visiting our nodes to print out the data. Because the rules say in an in order, I print my data on the left, then the middle, then the node, in the middle, the root, and then my right. So we keep peeking at the data value for each one of our nodes on the left. We've got to find that leaf that's on the left. The leftmost leaf of our tree. Does that make sense? Because it says left, root, right. So we can't even start printing data until we find that left that is the leaf. Our left that is the leaf is 54. So that's the first value we're going to print. Do you guys agree with that? It's just a little more complicated when you have this many levels. It doesn't change the rules though. Okay, so we do our left, 54. Then which one?
26.
26, because he's the parent node to my left. Does that make sense? And then what value? Since we're doing it in order, I did my left and my root.
71.
Then I do my right, so we do a 71. Try to visualize this and break it down into small individual packs of 3. The one parent with his 2 children. Okay, so we're done with this guy right here. We've already printed out 26 because we printed him out as a parent. So we don't need to print 26, even though he's the left to the 19. We already printed him as a parent in this relationship here. So we are done with our 26 node. Are you guys tracking on that?
Mm-hmm.
So that means we have to roll back up. If I printed my 26 and he's a child to 19, what's my next value I will print?
19.
And in order.
19.
19. Was it 22?
The 19,
Oh, 19.
isn't it? Because he's the parent to 26. So then I need my 19. Where would I go after 19?
22.
22.
Why 22?
It's in order.
Parent.
It's the parent.
19 doesn't have a right, does he?
No.
So there's nothing to print there. So we're done with our 19 as a parent. Now we have to deal with 19 as a child. So look at this level here. 19, his parent is 22, and 22 also has a right. So think about that relationship right there, just those three nodes. And then apply the rules. In order says, I get to visit my left, my root, and then my right. Okay, so we roll up to our 22. We've dealt with 22. We need to deal with 22 as the parent to 19. So we can print that. Where do I go after my 22 is visited?
33.
To my 33, because we got to do the right. Remember, look at that relationship. 22 has a left and a right. We printed our 19. We've printed our 22. Now we've got to go to our right and do our 33. Would I print him out yet?
No.
Why not?
He's a parent.
Because he's a parent, correct? So we can't print him yet because we're not done with him because he has children. So we're not going to print that 33 yet. Where are we going to go? What are we trying to find on the right side of 22?
Leaf.
The lowest level that's a left. We did that the first time with 22, the lowest level to the left. Got us all the way down here to our 54 before we could start printing our data. Okay, we've got to do the same thing with 22's right. 22's right is 33, but 33 has a left. His left is 14. 14 has a left. His left is 11. So can I print this number now?
Yeah.
Why can't I?
There's no
What
left.
have we found?
The leaf.
Leaf.
We found a leaf on the left of our node, correct? So now we're going to do our 11.
There's no left.
If I print my 11, what do I print next?
14.
The 14, because we're doing in order. In order says print my left, my root, and then my right. So now we can print our 14. Does 14 have a right?
Nope.
No, so we're done with it, correct? Now let's deal with 14 and its parent. 14 being a child of 33. Have we completely exhausted the left of 33?
Yeah.
Okay, so now we can move on to the right. But we got to do something before we move to the right. So we've printed our 14. What am I going to print next?
33.
My 33, because he's the root of 14. So now we're going to go to 87. Does 87 have children?
Yes.
So we got to follow that procedure again. We need to find the leaf, the leftmost leaf. We look at 87 and we know that he's not a leaf because he has two children. He has a left. The rules say on an in order, I do my left, my root, my right. So we need to print our 8. Now we can print our 87, followed by the 56. We've exhausted this relationship here. So now we can roll 87 back up to our 33. Now we can print
13. 13.
13. Are you guys tracking on that?
Mm-hmm.
Leftmost root, print the 87 on an 8. We printed our 87 because it's in order. We print our 56 because that's his right. We've done this relationship here. 87 is 33's right. We're done with that relationship there. We've already printed 33 because he is the parent in between 14 and 87. We've already done our 33. We've already done 33 as the parent to 22, because 33 is the right of 22. So now we roll all the way back up to our 13. We've exhausted the left of 13. Now we can print 13 as a parent. Where do we go next?
9.
To the 9. Can we print 9 out?
No.
Why? Because he's a parent. We have to find the leaf. Do we have a leftmost leaf on 9? No. We would, if we had a number there, we would have printed it, right? So we can't because there's nothing there. So what number gets printed next? Who says it's 9? Who thinks it's 75? Who doesn't care? Okay. Remember, we print the left, the root, and the right. 9 has no left, so we can print the 9. Now we can print his right, 75. We have completely exhausted the right from our 13. 13 is our left on our 3. We've exhausted everything on the left of the 3. Now we can print our 3 as an in order. Does that make sense?
Mm-hmm.
Because we're doing in order. Now we start going to the right, because the rules say on an in order, left, root, right. What is the first number that gets printed on the right of 3?
63.
Who thinks it's 63? Why is it 63?
It's the lowest level.
Yeah, it's the leftmost leaf.
It's the it's the
Most
leaf.
it's the
Something like that.
leftmost leaf of the right. It's the most left node subordinate to 28. So we come here to 28. We look, he has a left. So we know we have to deal with that left first because we're doing in order. 15 has a child. He has a left. We have to deal with that left first because we do left,
Oops.
root, come here. Or we're going to do nothing. That was just rude.
It's just like, come on.
Yeah, but he was like,
He said,
Feels like I'm tired of this crap.
wow.
that's not right.
It just said no. Nope.
That tree died.
I know, right? You guys ever seen the Godzilla thing where he's walking into the water? He's like, nope, nope. You ever seen that? You know what I'm talking about? Hey guys, all right, this is totally valuable information. It's actually the guy who I go to for my tattoo artist. So my tattoo artist is very, very talented, extremely talented. But his thing is so there's this deal where in Orlando, if the 13th falls on a Friday, some tattoo artists will do $13 tattoos. Okay, I don't know how many of you have tattoos or not, but I gotta tell you, I don't want a $13 tattoo. Because you get what you pay for, don't you?
Yeah.
Usually? But yeah, he won't even participate in it. So
Yeah.
the thing that cracks me up is yeah, did you guys see that?
No.
Yeah.
That was super cool. And Uncle took his niece to go see Frozen or something like that. She wanted to wear her princess dress, but she didn't want to be the only one. She didn't want to be the only one wearing a princess dress, so her uncle wore a dress too. That's so awesome. Coolest uncle ever.
hope we didn't go to Beltran, but it's maybe that's right.
They were in there.
Yeah.
Yeah, it's gonna be on the exam, so wait for
What's
it.
my tattoo artist's name?
Yeah.
I just gotta print this out. This guy's super crazy talented. So if you're into tattoos, it's actually, here we go. This is his opinion of $13 tattoos.
Oh.
Nope, not doing it. Okay, I love that picture. This applies to so many things in my life. Oh, you got it. I'll post it. Yes, sir. No, I don't have a financial statement. I didn't plan ahead yesterday, and I have to get a new toner cartridge for my printer. Okay, 4 minutes. Let's finish this in order. Just want you guys to suffer through this with me. Okay, so we got to our 3. So after our 3, we're going to print what?
63.
63, correct?
Right.
This is the leftmost leaf. And then 63 is the left of 10, so now we can do our 10. Does 10 have a right?
No.
No, so we're done with it. 10 is the left of 15. So we've already printed 10, so now we can print his parent, the 15. If he had a right, we would have printed his right next, but there isn't one. So we're done with 15. We printed out 15 as a parent node, so now we deal with him as a left to 28. Now that we've printed 15, we can do 28 because he's the root. Now we're going to go to the left where we have our 36, drill all the way down here to our leftmost leaf,
59.
and then we would go with our 59, and then his
69.
parent is 69, and then his right is 68. We look at 69 as a left child of 7, so now we can print our 7. So we've already printed out our 69. We would, if 7 had a right, we would print that next, but he doesn't, so we're done. So now we have 7. We've already printed 7 as a parent, so we look at him as the child for 36. So now we can print 36, and then we go to his right, and it ends at 44. So let's see if we got this correct. So we had 54, a 26, a 71, 19, 22, 11, 14, 33, 8, 87, 56, 13, 975, 363, 10, 15, 28, 59, 69, 68, 7, 36, and 44. So we got it, okay? Definitely go take a look at these. If you're in my lab sessions on Friday, we'll do the rest of this in lab. Quiz yourself and make sure that you understand how to do this because it's going to end up on exam 3 and or the foundation exam. There's no sign-in sheet today because I need toner. I don't have any. So